Section 3.6 is on page 215, talks about asymptotes. Asymptotes arise a lot in math. We have three types really. What an asymptote is a line that we get very close to. How close? Infinitely close. But never reach. So, here's a definition. It states if f of x approaches infinity or negative infinity as x approaches a number from the right or the left, then the line x equal whatever that x is a vertical asymptote. Graphically, we need to identify those, then algebraically we'll identify those as well. So we have two types of asymptotes that we focus on in this class. Vertical asymptotes, horizontal asymptotes. Vertical asymptotes is when you look at a value of x, in this case x equal 2, and you notice if you approach, that's what the theorem says, if f of x approaches infinity as x approaches 2. If I wanted to approach 2 and I am on this path, do you see as I get closer and closer to 2, this will get closer and closer to negative infinity? Or if I approach it from the right, well, if I'm taking the path from the right hand side, do you see this is going to go up all the way to infinity before I could reach that? So here we say the limit as x approaches 2. 2 is taking the place of c right now. From the left of 4 over, there's the function, x minus 2 cubed, that would be negative infinity. And if I take the limit as x approaches 2 from the right of 4 over x minus 2 squared, that would be a positive infinity. So you only need one of those. It says if y, that's y, where you're approaches infinity or negative infinity, as x approaches 2 in this case, from the right or the left, it doesn't matter, one of them will do, then we say x equal 2 is a vertical asymptote. So when I'm looking at number 4, I notice x equaling a negative 2 and x equaling a 2. Well, visually, I notice from the left of 2, that's going to approach infinity. That's sufficient. I don't have to go in and look at the right. I could, but, or just look at the right, not the left. It doesn't matter. If one of those ends is approaching infinity, automatically, that's a vertical asymptote. So graphically, glancing at this, so here it's therefore x equal to is a vertical asymptote. And here, since taking the limit as x approaches negative 2 from the left of f of x, there's f of x, equal infinity, automatically x equal negative 2 is a vertical asymptote. And that would be the yellowish. Again, you could have just did the blue. And if I tackle, say, the pink, that is, if I take the limit, what would that be? As x approaches 2 from the left of f of x, that also would be a negative infinity. Therefore, x equal 2 is a vertical asymptote. Now, algebraically, it's fairly simple to do. Limit-wise, it's fairly simple to do, and graphically, it's not that bad. Here's the deal. When I take a limit, our shortcut was to plug this in. And let me remind you really quick. Let me find it. I found it. It was section 1.5. You remember the rules for taking a limit? The shortcut, that is. The shortcut was, if you take a limit, you plug the value in. If you get a number, you're done. And if you get a number over 0, it does not exist. That's because the answer is either positive infinity or negative infinity. So anytime you get 1 over 0, that indicates that this is an asymptote. So, if I throw a negative 5 in there, do you see I'll get 1 over negative 5 plus 5, which is 1 over 0? Automatically, that tells me this is an asymptote. But they want us to find the limit here. And that's why they're finding the limit. To later on say, wait a minute, okay, I know what that is. That's infinity, that's negative infinity. So, it's fairly simple. All what you need to know is the denominator positive or negative. If the denominator is positive, then that's going to be positive infinity. And if the denominator is negative, that's going to be negative infinity. Now, no need to guess. We have a calculator, and you're allowed to use that on your exam. So if I take, again, I'm looking at negative 5, and from the left. So if I pick negative 5.01, and negative 5.001, and negative 5.0001. And if I get my calculator out, and what I want, again, I'm going to take, if you recall how we did this, it's been a while, negative 5.1, no, 5.01, right? There you go. We store that in the answer. Now we go in and we say take 1 divided by parentheses, the answer plus 5. I'm getting negative 100. And if I go in there and I plug in negative 5.001. Oops, yeah. And I go back, I'm getting negative 1,000. And if I go in there and I substitute a negative 5.0001. And if I evaluate, I'm getting negative 10,000. So can you guess what's going to happen? As x approaches negative 5 from the left, this is going to approach negative infinity. And if I do the same with this, again, if you throw the 3 in, you'll notice you'll get negative 0.5 divided by 0. That's infinity or negative infinity. Again, no need to guess, but that's a good way of predicting what your answer should be. If my answer is positive, if I plug in any value, I could do that by hand, really. If I pick x to be, and here I want it to be to the right, to the left of 3. Let's say 2.99. If I plug that in, again, anytime I get 1 over 0, my answer is either positive infinity or negative infinity. Well, all what I need is one value, 2.99. Wouldn't that be negative 0.5 divided by 2.99 minus 3? Isn't that negative 0.5 over negative 0.1? Negative over a negative, isn't that a positive? Positive infinity. Again, I don't have to make those guesses. I'm just going to use my calculator. A number to the left of 3, 2.9, 2.99, 2.999, and you get the idea. If I take 2.9 and input that, that's stored in my answer. Now if I input this in my calculator, if I take a negative 0.5 divided by answer minus 3, I'm getting a 5. If I throw in a 2.99, I'll get 50. If I replace x by 2.999 and evaluate, I'll get 500. So we get the idea that this is getting bigger and bigger. Eventually it's going to approach infinity. Now, on the next set of problems, so We did it using limits, we did it using a graph, and then given an equation. How do you know what the vertical asymptotes are? Actually, those are easy. Horizontal takes a bit of work. So here, if I look at this, determine all vertical asymptotes to the graph. Well, what you do, you simplify this. It's already simplified, so you look at the top and the bottom. And basically, it's always what makes the denominator equal 0. Basically, your domain. If I say, what's the domain on this? But be careful, domain after you simplify. That would be vertical asymptotes that would be what the denominator equals 0. If I said the denominator equals 0, x equals 0, and negative 7. Those two will be vertical asymptotes. And on number 10, the same deal. If I simplify the top and the bottom, the top factors into x minus x plus 7 into x minus 5. Okay, very good. Now, wouldn't those cancel out? So wouldn't f of x equal x plus 7 over x plus 5, provided x does not equal a 5? So what's the vertical asymptote? Here, the vertical asymptote would be, again, after you simplify, where does the denominator equal 0? There it is. Now the horizontal asymptote, again, each of those have an application, and we're going to do applications of each. If f of x, if f is a function, and L1 and L2 are real numbers, then if you take the limit as x approaches infinity and get a number, whether you go to positive or negative, as long as you get a number, we say those are horizontal asymptotes. And this is the idea. A horizontal asymptote is looking on the long run what happened. If you let the system run forever, what's going to happen? If I do this and I keep on working at it, keep on producing, keep on selling, keep on making units, what would happen on the long run to the cost, to the price, to the revenue? Now, something I need to show you. If I look at a number over x, I'm looking at as x approaches infinity or negative infinity. If I look at x equal 10, 1 over 10 is 0.1. If I look at x equal 100, 1 over 100 is 0.01. If I look at x equal 1,000, do we see that you're reaching 0? What if I picked negative 10 and negative 100 and negative 1,000? 1 over negative 10 is negative 0.1. 1 over negative 100 is negative 0.01. And 1 divided by negative 1,000 is negative 0.001. So do we agree that if we have a number over x and we take the limit as x approaches infinity, that's a 0? Or if we take the limit as x approaches negative infinity, that's also a 0? So any number over x, as x grows, if the denominator of the fraction grows, the whole fraction approaches 0. We're going to use that to our advantage and look at the next two problems and even the problems after that. It says find the infinite limit. So here's the deal. If I take a limit as x approaches a number, if I take the limit as x approaches infinity or the limit as x approaches negative infinity, if in my limit there is a number and an infinity and a number, as long as there is a single number and a single infinity, then that's really an asymptote. Here, taking the limit as x approaches negative infinity, we just agreed any number over x will approach 0. So you're left with 3 plus 0, which is 3. That would be your horizontal asymptote. And if I look at number 28, if I take the limit as x approaches positive infinity, well, any number over x will approach 0, and you're going to be left with 0 minus 9, which is a negative 9, and that makes this, again, a horizontal asymptote. So horizontal asymptote is easier to find than it is to find a vertical asymptote. Vertical asymptote, you might need to plug in a couple of numbers. Horizontal, you don't. It says find the horizontal asymptote, right, of the graph. Find the horizontal asymptote of the graph of the function. Okay, so this is what we do. We take the limit as x approaches infinity, and to use that to our advantage, we use a simple mathematical trick. We divide by the highest power term of the denominator. We divide each of those by x cubed. That's always the case, no exceptions. The limit as x approaches infinity. Well, the denominator, those cancel out. This cancels two of those. And we use that to our advantage. This is 5 over x plus 1 over x cubed. And we know that any quantity over x will approach 0. By dividing by the highest power term of the denominator, you're guaranteeing that there's no 0 in the denominator. So this is 0 over 10, and isn't 0 over any non-zero number? Isn't 0 over any non-zero number 0? I didn't say that right. Isn't 0 divided by any non-zero a 0? That's what I meant to say. So, fairly simple again how to do this. If I take the limit as x approaches infinity. So horizontal asymptote, always x approaches infinity or negative infinity. It works out the same regardless here, because of 1 over a positive or a negative will give you 0. It's really plus or minus 0, but 0 is the only number that has that property. Whether you say plus 0 or minus 0, you're saying the same thing. And here again, I'll divide by the highest power term of the denominator, which is x squared. So I'll divide the 1 by x squared, the x by x, negative 6x by x squared. Divide each term by x squared. And I'll get the limit as x approaches infinity of 2 minus 5 over x minus 12 over x squared all over 1 over x squared minus 6 over x minus 8. As x approaches infinity, any number over x will approach 0, and you notice we will get 2 minus 0 over 0 minus 8. We'll get 2 over negative 8, which is negative 1/4. So my horizontal asymptote is y equal negative 1/4. Vertical is x equal, horizontal is, I forgot to write it here. Horizontal asymptote is y equals 0. And here we go. The cost, C in dollars, for a company to recycle X tons of material is given by this. Find the average cost. A. The average cost is the cost function divided by X. That would be 1.25x plus 10,500, right? I could even say the cost function is 1.25x over x plus 10,500 divided by x. So the cost function is 1.25 plus 10,500 divided by x. That's part A. Part B says, find the cost when x is 100. Find the cost when x is 1,000. So if you want to recycle 100 units, how much would it cost? If you want to recycle 1,000 units, how much would it cost? If I take 100 and input that in, and if I take 1.25 plus 10,500 divided by my answer, $106.25. $106.25. The cost the cost of recycling, X is the number of tons of material. 100 ton of recyclable material will cost $106. What if I wanted to do 1,000? It'll cost $11.75. Something's not right. Let me take 100. Oh, yeah. That's because I didn't put units. See? $106. This is per ton. So if you want to recycle 100 tons, that cost is $106 per ton. If you want to recycle 1,000 tons, the cost is $11.75 per ton. And as you see, this is why you always get a deal if you buy more. If you buy 3, we'll give you 1 free. If you buy 1, we'll give you 1. Or if you buy 2, we'll give you 1 half price. The goal is to sell a lot, because the bigger the number is, the less cost it's going to be, and the more you're going to make. And how about part C? It says, determine the limit on the average cost function as x approaches infinity. Interpret the limit in the context of the problem. What is the limit as x approaches infinity of the cost function? That is the limit as x approaches infinity of 1.25 plus 10,500 divided by x. I could have used this equation all throughout, right? You really don't have to convert. You don't have to simplify, but it's easier this way. Since this is over x, that's going to approach 0, and I'm going to get this limit to be 1.25. What does that mean? That means if you are able to increase as the amount of recycle increase, that's what x is, the cost will level to $1.25 for each ton. Level reach. So it means if you could go high enough, if you can get enough tons to waste, you just need enough customers. Your cost is going to be $1.25. This person that's going to give you 100, right? You're gonna, it's instead of just recycling 100 and your cost is $106.25 per ton, now your cost is going to be $1.25. And then you could charge less or make more deals or stuff like that. Pretty cool, huh? And here's another example. This is of a vertical line. Here they gave us recycling bins, the cost in dollars of supplying recycling bins to percent of pollutant in rural township is modeled by this function, where x is between, p is between 0 and 100, because you know, pollutant can't go over more than 100. Find the cost of supplying bins to 20%, 50%, and 95% of the population. So, if you want to give bins, if only 20% of the population wants bins, then the cost would be 26,000 minus, so the cost function will be, actually, save time, I'm going to put that in my calculator, the usual. So that's what I'm going to put in my calculator, right? And I'm going to use P equal 20, P equal 50, and P equal 95. And if I go in there, let's go with 20 enter first. I'm using 26,000 times A divided by 100 minus A meaning the answer. I'll get the cost of supplying 20%, supplying Vince to 20% of the population will cost roughly, oops, I messed up. 20 we said. I clicked that again, it evaluated that. Okay, something's not right at all. What is 20? Okay. I don't think you have to do that, but I just want to make certain. $6,500. What if you want to supply 50%? Well, all you have to go in now and put 50 in. $26,000. What if I want to go for 95%? $49,400. Do you see what's happening? The price is going up, unlike what we were doing before. Before, when X was growing, this was the cost was decaying. Here, if you want to supply everybody in the population, it seems the price is going up. How about B? Find the limit as P approaches 100 from the left of 26,000 over 100 minus B. Well, it's fairly simple to do. All what I have to do is create a couple of numbers, and let's do that. Let me close this right here. Let me put and there's P, and there's 26,000 P divided by 100 minus B. So, if I'm gonna pick, this is 100, I'm approaching that from the left. If I go for P being 99, and then 99.9, 99.99, I'll see if this number is leveling off. And here's my calculator. I already have 2600p, right? So if I go for 99 enter and evaluate, I'll get 2,574,000. 2,574,000. If I go for 99, that's dollars. If I go for 99.9, 25,974, 25,974, 1, 2, 3. It'll cost 25 million. And if I go for 99.99, it's costing 25.99. Sorry, wrong key. 25.9974. And how many zeros? 3 zeros. 259,970,000. And if I wanted to interpret what that means, so look at that. 2 million, 25 million, 259. It seems there's no limit to this thing. Get it? No limit. That's what they use normally. That's what they mean. Interpret the limit in the context of the problem. Use a graphing device. We're not going to use a graphing device. If I look at the problem, so in terms of the problem, it seems the cost of supplying recycling bins to 100% or all of the population, the entire population, 100% of the population is unbounded, runs without a bound. It seems there's no limit to it. Is increasing. That's the word I was looking for. Increasing without a bound. Math, we say it's unbounded, but here you need the mathematical term. Without a bound. Right? If you plug in 99.999, this is going to go up to 2 billion. It's going to keep on going up. Anything you want to do for the entire population is costly. Right? Look at the healthcare right now. They're working so hard at it. Somebody has to absorb some of that cost. A big debate. It costs a lot. Alright, there's the homework.